All right, here are solutions for written problem 7 for Math 252. 4 parts here, but really what we're doing is Simpson's rule. So we have this curve, y equals 1 over x, and we're supposed to estimate the area underneath the curve from 1 to 3 using Simpson's rule with 8 approximations, so S8. And I kind of gave you Simpson's rule up here, so you might notice that we need to know what delta x is equal to. And delta x is equal to the same thing that it's been equal to, just b minus a over n. In this case, playing the role of b is 3, playing the role of a is 1, and playing the role of n is 8. So we get 2/8 or 1/4 for our value of delta x. I guess the next thing we need to know is what is xi equal to. Xi is always equal to a plus I delta x. So in this case, playing the role of a again is a 1, and delta x we just figured out was 1/4. So it's 1 plus a quarter of I. And what we will need to know is x0, x1, x2, x3, all the way up to x8, because we're trying to figure out S8 here. So I don't know that you really need to list all those things out, but I'm going to do it just so we have it handy. So x0, using this formula, I is just equal to 0, so it's just 1 plus a quarter of 0, which is just 1. And then x1, if we change the I into a 1, we get 1 plus 1/4, which is 5/4. And then x2 would be 1 plus 2/4, and maybe you can kind of see the pattern going on here. Oh, I'm just increasing by a quarter each time. So if I increase by a quarter, I get 6/4, aka 3/2, and then 7/4, and then 8/4, aka 2, and then 9/4, and then 10/4, aka 5/2, and then 11/4, and then finally 12/4, which is just 3. Oh yeah, that makes sense. I'm going from 1 to 3 here, which are the same as the bounds that I'm looking at here. I think I'm now ready to calculate S8. I'm going to go ahead and write the formula down here for you just so you have it for reference. A little bit tedious to write, but here it is. We got delta x divided by 3, and then we have all these f of x terms. Note that the coefficient on the first and the last one is just 1, and then we alternate between 4s and 2s sort of in the middle here, starting and ending with a 4. So since delta x is equal to 1/4, I have 1/4 divided by 3, so you can think about that as 1 divided by 4 divided by 3 divided by 1. And if you multiply by the reciprocal of the denominator there, I think you end up with 1/12. And then x0 is 1, so f of x0, since my function f of x is just 1 over x, would be 1 over 1, or just 1. And then I have 4 times f of x1, 1 over 5/4 is just 4/5. And then 2 times f of x2, 1 over 3/2 is just 2/3. And then 4 times f of x3, and 1 over 7/4 is just 4/7. And 2 times f of x4, 1 over 2 is a half. 4 times f of x5, 1 over 9/4 is 4/9. And 2 times f of x6, 1 over 5/2 is just 2/5. 4 times f of x7, 1 over 11/4 is 4/11. And then finally f of x8 is 1 over 3, or just 1/3. And all that's left to do now is kind of the arduous process of adding up all these different fractions. I don't know that you need to really watch me do that. I guess what I'm going to do is I'm going to first get rid of the coefficients. So 4 times 4/5 is 16/5. And 2 times 2/3 is 4/3, and so forth. And now I guess it's up to you. You could solve this algebraically. You could kind of combine like terms. So like 4/3 and 1/3 is 5/3, and 16/5 and 4/5 is 20/5, which is just 4, and make this a little bit easier, and then get a common denominator and deal with this horrible looking fraction. I don't know if that's really a good use of your time. I imagine most of you just pull out a calculator at this point. And if my calculator is to be trusted, you get 9137 over 8316, or about 1.0987. Okay, fine. Now I guess we could calculate the error bounds. For the error bounds with Simpson's rule, it's the fourth derivative of this function that we're interested in. If the function itself is 1 over x, or x to the negative 1 power, we can calculate derivatives by just using the power rule repeatedly. So taking this negative 1 down in front, we get negative x to the negative 2 power. Bringing the negative 2 down in front, we get 2x to the negative 3 power. Negative 3 down in front gives us negative 6x to the negative 4th power. And negative 4 down in front finally gives us 24x to the negative 5th power. Which you could rewrite as 24 over x to the 5th power if you wanted. And the reason you might want to write it that way is because what you're interested in is maximizing the absolute value of this expression when x is any number between 1 and 3. So in order to make this thing as large as possible, I got to make the denominator as small as possible. And to make this denominator as small as possible, well, let's see, if x is 3, I'm going to be dividing by a pretty big number. But if x is smaller and smaller and smaller, I'm going to be dividing by a smaller number, which will make the whole thing bigger. It looks like I want x to be equal to 1, which would make this thing equal to 24. I think the value of k that we will have is 24. So now I can calculate the error bounds by taking this 24 and plugging it into this formula. So b minus a is again 2, 3 minus 1 to the 5th power. and I have to divide that by 180 times n, which is 8 to the 4th power. And you could reduce this with the calculator if you felt like it. You could also notice that 24 is 3 times 8, so you can think about that as 3 times 2 cubed, because 2 cubed is the 8, times 2 to the 5th power. And then down in the denominator here, I can rewrite this 180 as 3 times 60. And you could reduce this further, but I think it won't even end up helping you. I just wanted to write it as 3 times 60 so I can cancel out the 3's. And then 8 is 2 to the 3rd power, so 8 to the 4th is 2 to the 3rd to the 4th, in other words, 2 to the 12th. And now I get the satisfying step of canceling. The 3's cancel out, and 2 to the 3rd and 2 to the 5th gives me 2 to the 8th. So 8 of these 12 2's can go away. And what I'm left with when all the dust settles is just 1 up top and a 60 times the 4 remaining 2's down on the bottom here. And 2 to the 4th is 16, and 16 times 6 is 96. So I think this is 1 over 960 is my error bound. So for step 3, I'm just using my answers from 1 and 2 to come up with an interval in which the real answer must fall. Well, all I got to do is take this as kind of the point estimate, the 9137 over 8316. You could also use the decimal approximation if you want, and then add or subtract my error bound 1 over 960. And I sure don't want to do that calculation, but my calculator doesn't mind. I quit with the fractions just because it gets so ugly and moved to decimals, rounded to 4 decimal places, just kind of arbitrarily. Hopefully that'll be enough. Adding and subtracting my error bounds to my point estimate gives me this interval right here. And then finally, step 4, where I can kind of check to see if I screwed this thing up and I have to do the whole thing over again. I'm supposed to calculate the exact value of this thing. Well, surprisingly, the exact value is a lot easier than calculating these estimations. It's just going to be the integral from 1 to 3 of 1 over x dx. And since the antiderivative of 1 over x is the natural log of the absolute value of x, I just need to evaluate that from 1 to 3. So what I get is just the natural log of 3 minus the natural log of 1. But the natural log of 1 is just 0, so I get the natural log of 3, which I can get a decimal approximation for to make sure it falls within these bounds. And it looks like it does, 1.0986 if I'm rounding to 4 decimal places. Pretty close to the original point estimate we had and well within these 2 bounds. The numbers in this problem got kind of nasty, sorry about that, but hopefully it kind of illustrates how Simpson's bound can give you a pretty good estimate as long as you're making your n relatively large. 8 ends up being relatively large for these purposes, and that when we use the error bounds, we do in fact create an interval in which the answer is guaranteed to fall.